Okay, today we will discuss problems on our bridges. Okay, here a problem it is given for us. An AC bridge is balanced at 2 kilohertz with the following components in the each arm. Arm AB is of 10 kilo ohms, BC is of 100 microfarads in series with the 10 kilo ohm, that is the resistance, and then arm AD is consisting of 50 kilo ohms. Find unknown impedance, that is R plus or minus JX in the arm of ADC if the detector is between BD. First you have to observe which are the arms are given. First you make sure of those terminals, that is A, B, C and D. Okay, first you fix this terminals. Then across AB a resistance is connected 10 kilo ohms. Across BC a capacitor 100 microfarad is connected to in series with the resistance of 100 kilo ohms. Then at AD 50 kilo ohms resistance is connected. We can take that as Z1, Z2, Z3, and across DC an unknown parameter is connected, that is taken as Zx. Okay, and across AC supply is connected. Across BD a detector is connected. Detector is between B and D. Okay, first you write what are the given parameters: Z1, Z2 and Z3, Z4. Here Z3 is going to be taken as a resistance in series. If it is series means minus J 1 divided by omega C3. Substitute for C3. Here it is of 100 kilo ohms and 2 pi into, here it is given F as a 2 kilohertz. You substitute that and you'll be getting as equation Z3 is equals to 100 into 10 raised to 3 minus J 0.7957 ohms. At balanced equation, we can write as Z1, Z4 is equals to Z2, Z3. Here, Z4 is going to be taken as Z2, Z3 divided by Z1. Substitute for each parameters, that is Z1, Z2, Z3 in the equation. Solve for this. After solving, you'll be getting as 500 into 10 raised to 3 minus J 3.9788 ohms. Observe here, this is your real value. This real value means it is of a resistance. The imaginary is of a, observe here, if you get a negative value, it will be of a capacitance. For that reason, Rx minus JXC. So Rx is of what? That is 500 kilo ohms, right? Then XC is equals to, it is taken as 3.9788. That is nothing but our XC I can write as 1 divided by F or 2 pi F into Cx. If I equate here, I want the value for Cx, capacitance, right? For that reason, take Cx this side. You'll be getting, can write as 1 divided by 2 pi into F is 2 kilohertz, then into 3.9788. If you calculate here, you will be getting as 20 microfarad. This question will be asking for 6 marks in the examination. First you write what are all the given terminals, at what terminal which one is connected, and find out what is our unknown parameter. Okay, we'll go for next set of bridge, that is a Haste bridge. These are all the basic equations what is required to solve the problems. Okay, in the theory part we learned how we got these equations. Okay, here the first problem based on Haste bridge is of calculate the unknown inductance and resistance measured by the Haste bridge. This bridge elements at the balance condition are R1 is equals to 5.1 kilo ohm, C1 is equals to 2 microfarad, R2 is equals to 7.9 kilo ohms, R3 is equals to 790 ohms. The supply angular frequency is of 1000 radians per second. Okay, what you have to do, all the parameters are already given for us, just you substitute in the equation, that is Rx. Rx is taken as omega square R1 C1 square R2 R3 divided by 1 plus omega square R1 square C1 square. We got every parameter equation are already given for us, just you substitute. Omega is 1000 radians per second. Angular frequency only directly it's given, for that reason just substitute omega value as 1000 square. R1 is of 5.1 K. Then C1 is of 2 microfarad square. It's a square, okay? Square into R2 is of 7.9 kilo. Then R3 is of 790 divided by 1 plus 1000 square. 5.1, that is R1 square. Then C1 square. Substitute, you will be getting as Rx as 1.212 kilo ohms. Then Lx as, this is the equation you have to use, R2, R3, C1 divided by 1 plus omega square, R1 square, C1 square. Substitute for each parameters, R2, R3, C1, and also substitute for the denominator part. After solving, you will be getting as 118.83 millihenry. These are all the unknown resistance and inductance of the Haste bridge. Okay. Then we go with the solving of the Anderson's bridge. In the Anderson's bridge, these are all the basic equations. Lx is equals to C into R3 divided by R4, R2 small r plus R4 small r plus R2 R4. R1 is equals to R2 R3 divided by R4. Here a problem it is given for us. What is the problem? The arms of the 5-node bridge are as follows. Arm AB, an unknown impedance, that is R1, L1, in series with a non-variable resistor R1, small R1, it is connected across A, B. Okay. Then across BC, a non-inductive resistor R3 is connected with 100 ohm. Across CD, a non-inductive resistor R4, 200 ohm. Across DA, a non-inductive resistance 250 ohms, it is connected. Across DE, a variable non-inductive resistor small r is connected. Arm EC, a lossless capacitor C is equals to 1 microfarad, it is connected. An AC supply is connected between E and C. Detector is between B and E. Calculate the resistance R1 and inductance L1 when under balance condition. R1 is given as 43.1 ohm and small r is given as 229.7 ohms. Based on the given parameter, first we will draw the bridge. Okay, first they are telling across AB, what it is connected, an unknown impedance, that is R1, L1 is connected along with the resistor R1. Yes, variable resistor. This is your AB. Across BC, and resistor is connected. Across DA 250 ohms resistor is connected. Across DE, this is DE. Across DE, a resistor R is connected. Then across EC, this is E and C. Across E and C, a capacitor is connected with 1 microfarad. Okay, and they given the values for R1 and also for the R. This is our bridge. This is nothing but our Anderson's bridge. First, we'll go with the equation, that is R1 is equals to R2 R3 divided by R4 minus of R1. Okay. What you will be getting, substitute for R2 R3. R2 is of 250, R3 is of 100. For R3 is of 100 divided by R4 is of 200 minus this R1 is connected in series, right? For that reason, the unknown parameter equation is of this minus of R1. We'll be getting a R1 resistance for that reason. 43.1, you will be, after substituting, you will be getting as 81.9 ohm. Then for inductance, what is the inductance? Lx is equals to CR3 R4, R1R, R2R, R4R, and R2 R4. Same thing, here you substitute. C is of 1 micro, R3 is of 100, R2 is of 250, small r it's given for us, that is 229.7 plus R4 is of 200, again R you substitute, then R2 is of 250 and R4 is of 200 divided by R4, that is 200. If you substitute and if you solve here, you'll be getting as 76.6825 millihenry. First you have to go for the at which terminal what it is connected. Okay, only remember here across unknown parameter is one more variable resistance, small resistance is connected. If you subtract from the balanced equation, you will be getting your unknown parameter, that is R1. Okay, this is how you have to solve the problem based on the Anderson's bridge. And here one more problem it is given for us. An Anderson's bridge is arranged as follows. Branch AB is an inductive resistor. Branches BC, okay, and ED are variable non-reactive resistors. Branches CD and DA are non-reactive resistors of 200 ohm each. Branch CE is a 1 microfarad capacitor. The supply is connected between A and C, while the detector is connected between B and E. Balance is obtained when the resistance of BC is 400 ohm and that of DE is 500 ohm. What you have to, this is the given parameters, and we have to calculate the resistance and the inductance of the bridge. First you come across here, this connection is not there. Okay, here across AB an unknown parameter R1 and Lx is connected. Across BC R3, that is 400 ohms, it is connected. Across DC R4 connected with the 200 ohm. Across AD again R2 is connected with the 200 ohm. Here a small resistance R is connected. This small R is of 500 ohm. Here it is given. Okay, DA is of small r and EC is of one capacitor, that is of a 1 microfarad. What is the based on the given parameters? We draw on the Anderson's bridge. Next what you have to do? We have to find what is Lx and what is our R1. Just substitute Lx is equals to C capacitor value into R3 divided by R4, R2 R plus R4 R plus R2 R4. Substitute for each of the parameters from the bridge and you will be getting the inductance value as 0.68 Henry and R1 as R2 R3 divided by R4. Here nothing extra is connected here, just you substitute the values for resistance R2, R3 and R4 as 200 into 400 divided by 200, you will be getting as 400 ohms. This is what the Anderson's bridge problem. Here one more problem it is given for us. In an Anderson bridge, for the measurement of inductance, the arm AB consists of an unknown inductance of L and a resistance R. A known variable resistance in arm BC and fixed resistance of 600 ohm in arm CD and DA. Okay, so across CD, a variable resistance is connected and fixed resistance of DA, both are of having the value 600 ohm. A known variable resistance in arm DE and a condenser with the fixed capacitor of 1 microfarad in arm CE. The supply with frequency of 100 Hz is connected across AC and detector is between B and E. If the balance is obtained with a resistance of 400 ohm in arm DE and resistance of 800 in arm BC, determine the value of L and R. Based on the given parameters, we have to go for the construction. Observe here, this is what the bridge across across AB, an unknown parameter, resistance and inductance are connected. Across AD, it is connected as R2, and across R4, here it is connected as across arm DC, R4 is connected. Across CB, R3 is connected, it's a variable. And across CE, capacitor, and across DE a small resistance is connected. The unknown parameters of LA Rx is equals to that is nothing but R1 is equals to R2 is of what value? R2 is of 600. This value 600. Then R3 is of 800. R3 is of 800 value. Here it is given 800. And then R4, if these both are having same values, that is CD and DA. CD and DA. For that reason, it is both are same values, that is 600. If you solve, you will be getting as 800. That is your R1. What is our LX? C into R3 divided by R4. R2 into R plus R4 into R plus R2 R4 whole divided by R4. Just substitute for each values. Capacitor is taken as 1 microfarad. 1 into 10 raised to minus 6 and R3 is of 800. Then R2 is of 600 and small r is of 400. 100 hertz is given. Here it is given resistance 400. Okay, small r is given as 400 plus R4 is of 600. Again R is of 400. R2 is of 600 into R4 is also having the same value 600 divided by R4 is of 600. If you substitute, you'll be getting as 1.12 Henry. Everything it is given, just you construct in a proper way so that you can get the correct values for each of the resistances, and for the unknown resistance value you can find, and also for the unknown inductance also you can find out. Next is a desorted bridge. This is the equation C1 is equals to C2 R4 divided by R1. Here a question is given for a desorted bridge. A four arm of a bridge are arm AB and imperfect capacitor C1 with an equivalent series resistance of R1. Arm BC a non-inductive resistance of R3. Arm CD a non-inductive resistance R4. Arm DA an imperfect resistor C2 with an equivalent series resistance of R2 in series with a resistance R2. It is connected. A supply of 450 Hz is given between terminal A and C, and the detector is connected between B and D. At balanced, R2 is going to be taken as 4.8 ohms, R3 is taken as 200 ohm, R4 is taken as 2850 ohms, and C2 is a 0.5 microfarads, and R2 is taken as 0.4 ohms. Calculate the value of C1 and R1 and also of the dissipating factor of this capacitor. This is what the given problem. Here the construction is done. Across AB, a resistance R1 and C1 is connected. Across BC, a resistance R3 is connected. Across CD, R4 is connected, and across AD, resistance and small resistance R2 and capacitor is connected. This is what the construction. In this, Z1 is going to be taken as R1, small r1 minus J1 by omega C1 ohm, and R2 is taken as, because here R2 is in series with the small r2, for that reason R2 plus R2 minus J1 divided by omega C2, because capacitor is connected. For that reason, here you have to write as J1 divided by omega C2. Substitute for R2 and small r2, 4.8 and 0.4 minus J divided by 2 pi. F is given as 450 Hertz here into C2 is of 0.5 into 10 raised to minus 6. If you solve, you will be getting as 5.2 minus J 707.3553 ohms. It is in a polar form, sorry, rectangle form, converted to polar form. So you'll be getting as 707.3744 with the angle of minus 89.5788 degree ohms. And for Z3, it is of only the resistance part. So you'll be getting as 200 plus J, imaginary part will be 0, 200 at an angle of 0 degree, and Z4 is of 208.50 plus J as 0 ohms because it is not having any uh, reactance terms. Okay, for that reason, then you'll be getting as 2850 with the 0 degree. At a bridge balance, no current flows through the galvanometer. Yes, based on that, I can write here as I1 is equals to voltage divided by these two are Z1 and Z3 will be in a series. For that reason, E divided by Z1 plus Z3, and across I2, this I2, okay, that is going to be taken as E divided by Z2 plus Z4. When it's in a balanced, I1 Z1 is equals to I2 Z2 for null in deflection of the detector. Based on that, I can write here as E into Z1 divided by Z1 Z plus 3 is equals to E Z2 divided by Z2 plus Z4. You'll be getting a balanced equation here. Here these two will get cancelled off. Or else you can directly write the balanced equation. That is Z1 Z4 is equals to Z2 Z3. After that, what you have to do? Just substitute for Z1, Z4, Z2 and Z3 in the given equation. So you'll be getting as this equation. After this, solve for this. Take this whole part towards this and calculate here. You'll be getting as R1 minus J 1 by omega C. This will be remains as it is equals to, if I divide here, I'll be getting as 49.6403 with angle of minus 89.5788 degrees. You solve here. Okay, after solving, you will be getting this result. This, what I can write, again converted into a rectangular form, I can get as 0.3649 minus J 49.6389 ohms. Comparing both sides in terms of this is your real value and this is your imaginary value. The real value is of your equating a real part to the real one, that is R1 is going to be taken as 0.3649. Then here is also minus and here also minus. So if I equate the imaginary parts, then I will be getting as 1 divided by omega C1 is equals to 49.6389. Then what we want? We want what is our capacitor. So shift the capacitor here and this value towards this side. You'll be getting as C1 is equals to 1 divided by 2 pi into F is of 450 into 49.6389. So you'll be getting as 7.125 microfarad. Okay, calculate here. You'll be getting this value. Then what is the dissipating factor? That is dissipating factor is taken as omega R1 C1. So omega is of 2 pi F, 2 pi into 450, and C1 R1 is given as 0.3649 and C1 is taken as 7.125 into 10 raised to minus 6 micro, right? If you calculate, and you will be getting as a dissipating factor as 0.007351. This is a problem based on the Haste bridge. We'll stop here. We'll continue in the next class.